Okay, okay. Thank you, thank you. So only Acha Pathak has joined. Very good. At least one person is there. And let me see. Pathak, you are doing seriously or not this course now? What is? Are you attending, solving the assignments?
Yes, sir, solving. Up to 5th, I have submitted.
Up to you have submitted?
Up to 5th.
Up to 5th you have submitted. Okay, okay, fine. So maybe you try to take exam also. No? And
yes.
So I think that here in the live session, I am seeing that not many people have joined actually, that this one. So maybe I can discuss with you only for some time, and I show that how many lectures now have been covered
till 19.
Let me just share my screen. Okay, till 19. So, huh?
Till 19.
19 is finished. So 20 lectures are only there.
20 lectures are there. Only 1 week is left. Week 8 is not yet live. Week 8 are live.
Acha, week 8 is not. Acha, so only one lecture in that week. Huh? Only one lecture. Yes, yes. Acha, let us see.
Non-traditional.
Okay, okay, okay. So let me just go to that MOOC. Okay. So it is. MOOC. Let me just go to this one. 223 V1 course. And no, first I should go to PPTeach. No? Okay, PPTeach. Okay. Where are PPTeach? This one. Okay, assignment, exam, video, queries, figures, PPTeach. Yes. So I think we discussed up to 11th lecture, na? And this is 12th lecture here. Okay. So yeah. So let me just go to this team. Okay. ये क्या minimize कर दिए? Yes. Pathak, I am just sharing one slide and I show you some points actually there. Nah, which you have to pay attention. Not just general thing. Okay, let me just go to share. Nah. Okay, screen. Okay, entire screen. Nah. Entire screen. I say share. Okay. So better to share screen. Pathak, is it visible? That's my slide. Where
yes,
I
yes.
am marking. So thermal aspects.
Yeah.
Thermal aspects. Okay. So the
yes.
thermal aspects actually other things you can basically read in the book and in the lectures also. But I am telling that in this I had added one thing about that Johnson-Cook model actually. No? That how the flow stress is dependent on the strain rate and temperature. If strain rate increases, the flow stress will increase, and with increasing temperature it decreases, and with strain also it increases. Then this derivation I did for heat conduction. Now in the heat conduction derivation, if you see that here, if suppose there is a moving material, that means material is moving and temperature is also changing. So entire derivation is there, but I want to draw your attention to this equation, heat transfer equation, very important equation, that here you have K by rho C, theta is temperature, del square theta by del x square, del square theta by del y square, like that. And then plus Q by rho C, but you are having rate of change del theta by del tau. Tau is the time, but you have Vx del theta by del x, Vy del theta by del y, Vz del theta by del z. So these are convective type of terms actually. That means because of the flow velocity you are getting that. Otherwise heat conduction equation, in most of the heat transfer books it is only told about this, that these terms, and then you have got about this one, rate of heat change, but this term is added because the material is flowing. Okay, so this is very important to pay attention. And then we are also mentioning one point, that suppose you do plastic deformation, then most of the energy of the plastic deformation goes as a heat. So but not all, about 90% in some cases 95%. So in some cases, maybe I don't know, that means some different also, because it depends on many factors. But usually most of the materials people believe that it is between 0.9 to 1. So remaining, you know, that is very small fraction goes to increase the internal energy. And then about the temperature, so these are like, how do you find out the temperature rise? You know, if total power consumption is FC into V, and the power is lost due to plastic deformation, as well as in the secondary shear zone, that means due to friction also. And these are some expressions based on that, that how much is the power temperature rise. And then these are somewhat empirical type of expressions. Okay, that because moving heat source problem is very difficult as such, so we use empirical equations and we get, say for example, we are getting the final temperature as high as something like 900 degrees centigrade. How we are getting that? Means there is some theta 0 means initial temperature of the workpiece, then theta p is the heat generation in primary zone. So you see in primary zone about 337, but secondary zone means chip is riding on the rake face. So therefore lot of heat is generated there and temperature rise is 552. So that is why highest temperature is achieved at the rake, and that is why you get crater wear at the rake surface. So this is a little more analytical expression that you can find out temperature distribution, 3B analytical expression. And then we have discussed that how you can measure the temperature. One is that you can put some material whose color changes. No? Yeah. Hello?
Sir, sir, if we use the means tool material
Yes.
of different, suppose high speed steel, then carbide, then
Okay.
will the temperature generation will be different?
Yes, yes, naturally, because those properties are different, na. Because see, suppose you have highly conductive tool material, then the you know, heat will pass away easily. But if you have the thermal conductivity is poor, then all the heat will be concentrated only at the top surface. So temperature will be very high. So that is why it is a requirement that conductivity should also be high. You see that here even the conductivity term is also coming into the expression when we are calculating the temperature generation, na? And so naturally the tool material has effect on that actually, na? That means this will be this one. So you should have highly conductive material, but carbide tools are having sometimes very poor conductivity in comparison to high speed steel. Okay, so that is how it will be. Okay. So temperature, it will definitely it will be dependent. So this is by calorimetric one, and these are the you can measure the actually temperature generation measurement is very difficult here we use the thermocouple type of thing. In fact, I asked some students to make this setup and measure the temperature, but it was very difficult because the chips are coming and it will create a lot of noise. So measurement of temperature like this, which is considered a classical technique, is also very difficult. So then a thermocouple technique can be used, but it is this one. So this is a technique of infrared photography technique. Nowadays we have infrared camera also, to some extent they can actually tell the temperature, and these are the effect of various parameters like cutting velocity increases, then temperature will increase, and this is a tool temperature versus tool rake angle. Even rake angle has effect on the tool temperature, and even clearance angle also has effect of that, cutting edge angle, and then cutting temperature, and this is what nose radius, effect of the nose radius. So you see that if the nose radius is increasing, then you know cutting temperature is decreasing. And now proper selection of material and geometry of cutting tool, physical or chemical. So these are the techniques: physical vapor deposition and chemical vapor deposition. They coating of high speed steel and carbide tools help reduce temperature by reducing friction. So what you asked is comes from that also. That means one way is that, of course, the coatings can reduce the friction. And in the high speed machining of steel, lesser heat and cutting temperature develop if machined by CB and tools, as they produce lesser cutting force. Okay, so it is not just one factor. By enhancing the thermal conductivity of ceramic tools, as I was telling, the thermal conductivity should be very high so that heat dissipates and it doesn't concentrate on the top. So we can add in that ceramic tool these materials like metals, carbides in an Al2O3 or Si3 in whole matrix. Okay, so and the tool geometry also, of course, is very important. Then optimum selection of cutting velocity and heat combination without sacrificing MRR. Okay, so this is also very important. Cutting fluids so that the heat is carried away. Lubrication also. So these are the properties of lubricant, and this is yeah, and this is what complete the mechanism of that cutting action. This is cutting velocity versus this is okay, cutting velocity, and this is Cp by Cn. Okay, that for extreme pressure, and this one. So this one, and then this is so these are types of cutting fluids, methods of application of cutting fluids. Nowadays, lot of papers have been published on MQL also, minimum quantity lubrication actually. That is also almost saturated. Okay, that means, but then let us go to the next sheet. Okay, lecture 12, 12, 13, 13, it is, yeah. In the 13, we are telling about tool wear and tool life. Okay, so different type of wear mechanisms have been explained, and then particular thing is that crater wear. Crater means pit. So there is a pit on the rake surface because of high temperature. It is a diffusion is the main mechanism, and then this is frank wear, which is on the clearance surface. Dimensional accuracy is affected by the frank wear, not by the crater wear. So because this is and these are the practically when I did experiments, then I got this type of graph. Okay, crater wear, how it increases. Tool life, very difficult to define even tool life. Means some people define important. So there, but usually people in for solving numerical type problem, people used to take frank wear criteria. But there are many. Tool life is also a subjective term. It can be defined in many ways, and this is the Taylor's tool life equation. And tool life is related to cutting temperature. Okay, so T theta m is equal to C2. Rake angle, what is the effect of the rake angle, frank angle, and it is a side cutting edge angle, node radius. Tool material should have, see, hardness, tough enough to withstand shock and fracture, should have high resistance to wearing action, coefficient of friction should be low, and you see thermal conductivity and specific heat both should be high. Why the thermal conductivity should be high? So that the heat gets dissipated soon. And why specific heat should be high? So that lot of heat is there, but that increases less temperature. Specific heat more means less temperature rise. Thermal expansion obviously should be low. So these are the various type of tool materials are there. They have been described here. And cemented carbide, etc., CBN. These are the tools very common. And we about 5 micrometer thin coating also is applied, and hardness and all that type of. This is generally the as a thumb rule, cutting speed as hardness of the material increases, then cutting speed should be decreased. So this type of empirical relation. Cutting fluids are there, and this is estimation of tool life. So suppose we have formula Vt to the power n equal to C, that constant n is given like this. Okay, for different materials it is different. And quick tool life is testing devices based on the Frank wheel. And then we have told some other type of suppose there is a variable speed machining, then how you should calculate the tool life. This has been told. Then we told about machinability. Actually, this chapter has been nicely written in this book, Introduction to Machining Science by G.K. Lal. Okay, so you can refer that thing about this one. And now lecture 14. This was that is optimization. Okay, so optimization is even that this is also one area which is very saturated. Means lots of thousands of people have been and then tool, this one, cutting cost and tool cost, right? So tool cost, so these are the three components. So tool cost and tool changing time increase with increase in cutting speed, and cutting cost and cutting time decrease. Okay, so two opposing effect. That's why this idea. Okay, so this is cutting speed for maximum production rate, restriction on the cutting conditions, surface finish restriction, lot of constraint. So people have been using actually, and this is multi-pass optimization. Okay. Now I have obtained one means interesting observation that most of the time that even if you do by heuristics also, then you can know the answer. No? Because as a thumb rule, cutting speed should be as high as possible. After that feed, and after that depth of cut, means depth of cut has the less influence. Okay, so means depth of cut, if you want, you can keep very high also. Okay, but the cutting velocity should be if you want to have high production rate, then cutting velocity should be high. For minimum cost of machining, cutting velocity can be less, so that your tool cost is not there. I have made some thing that by heuristics, but even then people have been solving the problems, and these have been getting obvious result. So this problem has acted more like a benchmark problem for testing the optimization algorithm, rather than contributing much to machining science actually. No? So anyway, so I am telling that this area, if somebody wants to take up any PhD topic in this area, then he has to be very carefully that this because this is more or less saturated. Okay, but of course, if one can use the new techniques, then matter is different. Okay, and then what happens that here, this one, let me just see that here, lecture 15 we have discussed. Yeah, 15. Now, practical machining operation. So these are some practical machining operations. This is turning, and I want to emphasize again how the cutting is taking place, and how the side cutting edge is taking the chips, and how the chip thickness is related to the feed. It is feed time cosine of that angle, and depth of cut is related to the width actually, not the other way around. That feed is, chip thickness is dependent on the feed, because cutting edge is this. It is not, the cutting edge is not that this is secondary edge, auxiliary cutting edge, which is not participating much. So we consider that this is the main cutting edge, and this is how that it is cutting. Okay, so this is very important, that P is equal to feed times cos gamma s, and width is equal to d divided by cos gamma s. Okay, so and in three-dimensional case, you will be having three components of the forces, and this is the resultant one. And then what happens that generally these are empirical expressions, that Fp is dependent on AP, some constant, and Fxp into dyp, and similarly Fq, and then this is Fr. Now this point is that So in many mechanistic models, this type of relations are used. And these coefficients can be obtained in empirical way. So it is something like semi-analytical type of approach actually. So because that gives you little reasonable results, and these are the power consumption, surface finish. Okay. So these expressions are also taught, but they are very ideal type of surface roughness expressions. Okay. You have like H is equal to F divided by tan gamma S plus cot gamma E. Okay, if there is no node radius. If node radius is there, then H is equal to F square by A tal. These are ideal one. Practically, the surface roughness will be much more. No? And you see that with feed, the surface roughness is always increasing. But if you take very small feed, then surface roughness can be very high also, because that time the cutting action will not take place. Okay. And similarly, the surface roughness, if you increase the cutting speed, initially it increases because of the built-up edge, etc. And then after that it decreases. Okay. So this type of behavior, see, these are my own MTech student has done. This is a highly cited paper also he has published. Experiments of turning with TIN coated carbide tool. And you see that when my feed was very small, 0.05, then my surface roughness was high. And with feed, it started decreasing. Actually, prediction is that if you use by formula, then with feed it should increase, but it is decreasing. Only after this one, something like 0.12 or some millimeter per revolution, then that formula became correct. That means it is like that. So you should not have too small that type of. So these are the real experiments done at IIT Guwahati. Here also you see that. हाँ, मैं थोड़ा मूक कोर्स में हूँ अभी ना, कुछ क्या, हाँ बताइए। मीटिंग तो इसमें है कॉन्फ्रेंस हॉल में, कॉन्फ्रेंस हॉल में, हाँ कॉन्फ्रेंस हॉल, ओके, हाँ सेंटर में, सेंटर में, हाँ हाँ हाँ। नहीं, मैं थोड़ा मूक का मेरा चल रहा है, एनपीटीईएल का इंटरेक्टिव सेशन है ना, तो इसमें मैं हूँ ना, ओके, या वो यहाँ से टाइम मिलेगा तो जाऊंगा मैं वहाँ ना, ठीक है, ओके ओके, ठीक है, ठीक, ओके ओके, थैंक यस। नहीं, 4 में से कोई एक होगा ना, हाँ, मेरा लाइव सेशन चल रहा थोड़ा, मैं वक्त देता हूँ ये, ओके ओके। So you see that here also the same type of, you also get a dip here. These are in fact, now you will hardly find out in any textbook. Actually, MC Shah has discussed this in his book, but not many books discuss this. And these are our own experiments we did in 2002. And here we did not find that 238. Here with feed it is always increasing, but you see that this is sometime some dipping and something like that also we are getting. And then this is shaping and planing, similar type of thing, force components, and you see surface finish here, similar type of behavior. Then these are numerical problems. You can practice these here. And yes, so these are problems here. So this was about that thing. Now I am going to this one. Let us see. Go to that another one. 16. Okay. So 16.1. Yes. Practical milling and this one. Now milling and building. Now multi-point cutting processes. So up milling, down milling. That anyway, Pathak, you must be teaching to diploma students. Okay. Up milling, down milling is very important. Usually undefined chip thickness. Here the chip thickness keeps on changing, and it is from 0 to this one, and roughly the length is given by this. Volume of the chip is this one. Approximately the mean chip thickness is half the maximum chip thickness. And so these type of about the milling. Generally, people don't study much about milling; they only study turning. But milling is also very interesting, and here you see that number of teeth is very important. And suppose you have 0 helix angle, then you see force increases, and then after that there is a gap, then again it comes like that. And if you have more number of teeth, then this force has finished, by that time another one has come. And then what happens that if you have more number of teeth, then you have, so if you increase the number of teeth, then more or less cutting action will be uniform, but you will not get enough space between the teeth, and so chips may also get clogged. So that is why you should have optimum number of teeth. Okay, and this is the effect of helix angle. Why we want to have helical type of tooth, so that for fluctuation in force is reduced. Okay, because helical action, one place that if the force will be low, and other side it will be high, and this is face milling. Okay, surface finish similar to that. Here also the expression comes. So you have seen that surface roughness. Building process, twist drill, and this is in building process. Geometry itself is very interesting. So you have to study that normal rake angle itself keeps on changing with radius. Okay, with it varies with the distance, and this is chip formation in building forces, and the forces because of the chisel component also, that because this one. So this is the geometry of this one. It is dependent on the field helix angle. So these are the things here. You can slowly you can study, because I am just giving exposure here. Grinding is a very interesting topic, and even MC Saj book it is nicely explained, and it is also explained in GK Lal's book. It has been very nicely explained. In other books it is not that much explained, because GK Lal did, I think, PhD also in the same area, grinding. So grinding is the process. Here we have chips and abrasives, grain size, bond material, and grade. It is very interesting that hard feel means that hardness of the wheel means bonding strength. Okay, so hard wheel should be used for cutting the soft material and vice versa. And these are the grinding wheel specification, and this is the mechanics of the grinding, how the cutting take place. So it is similar to milling, and therefore you get expression also like a milling. Chip length is proportional to depth of cut, and it is proportional to diameter, and it is this one, chip thickness. So cutting point, that means how many cutting points are in per area, and here it is also described that how do we measure. Even measuring the how many grains are in that area may be little challenging task. One method is that suppose you take a black paint, and on that you move that grinding wheel, then you can get some idea from that. That means there it will make some mark there. Okay, and grinding force and specification, specific energy. Here it is emphasized that if the chip thickness is very small, then the specific energy will be very high. Okay, so we will wear different type of wears. Bond fracture wear. Bond should not be too strong also. Sometimes bond should release the wheels. That's why grinding is called self-sharpening action. Okay, and grinding temperature. Okay, this is surface roughness. So you see the expression for surface roughness. It is showing that V divided by V. That means if the field speed is high, then it will be fast. Surface roughness will be less. And this is given in terms of the chip thickness and divided by 16D. That means if depth of cut is more, then you get less surface finish. Okay, that is what this one. And then another lecture is this one. 17 we finished now. 18 surface finish in machining. This we have not covered. Yeah, this one. Okay. Ideal roughness. Yes. So total roughness, you see, it can be very high, but ideal roughness is much less. And this is lapping, honing, super finishing, polishing. So this is a lapping type of tool. Lapping is accomplished by abrasives in the range of 120 to 1200 mesh, and with lapping pressure of this much. Lap is generally made of material softer than work material, and abrasives are loosely bonded, are held by carrier fluid, and then this is wrapping. Then you have got hardening. This is wrapping, hardening. Mostly that, you know, IC engine cylinders are sometimes they do hardening. It can make texture also there. And then super finishing. And then after that, polishing, buffing, these magnetic field assisted polishing. These are the things about this one. And we are not having any numerical here. But lecture number CNC machines. This has been covered.
Yes,
CNC machines. Okay, this is one CNC machine at IIT Guwahati only, and this is these are typical CNC machines. And here you know advantages and now programming etc. So mostly G code and M code that you can teach to students. Okay, in code they can write their program, and this one is yeah, 2-digit number G00. These are the some codes. M06 is tool change. So some terms are there. Now, what are the main important thing is this one, that CNC. You know that Pathak ji, you know what is a bar screw in CNC machine? Bar screw.
Yeah,
Yes,
ball screw.
Yes. What is that?
Sir, so that the sliding takes place smoothly because of that ball screw nut that is used.
Oh, so it is in the, that means there are some small balls that keep moving on the helical path. Okay, helical path
Yeah,
they move. Okay,
recirculating.
recirculating. Yes, they are recirculating type of thing, and usually we use two nuts actually. That is called double nut compensation. Okay, that there will be two nuts and in between we'll put a special. So one nut is, you know, that a line means pushed on one side, left hand side, others is pushed on the right hand side. So that means these bars are against each other. So this type of arrangement we do, that this type of preloading we do to minimize the bypass. Okay, otherwise there will be bypass. So that is called double nut compensation. Okay, and then okay, now then what happens that here yeah, okay, let us say that this one. Okay, okay, now this one, it is like this. So one issue is that what is that thing? This has gone here. Okay, 19 linear motion guide wage. Okay, these are also basically balls there, angular contact ball bearings. But preloading is very important in for accuracy. That means already you apply some load. Then drive means stepper motor, servo motor, AC DC. Sensors means optical encoder, linear scale, and resolver. They work on the magnetic, this one. And then hydraulic and pneumatic system, of course. There are a lot of hydraulic and pneumatic system. These are the hardware items of CNC machine. And lastly, we have to cover one lecture, which will be last lecture, advanced machining processes. Okay. So we are just giving idea, mechanical process, chemical process, electrochemical, thermal based machining, iron beam machining. Many people think that iron beam machining is also a thermal process, but it is not a thermal process. Here the material is removed by sputtering of workpiece atoms due to bombardment of a focused iron beam. But I have seen most of the people confused. They think iron beam machining is like electron beam machining. Electron beam machining is similar to laser beam machining. This is dependent on this one. And so we are just telling these processes will be covering ultrasonic machining, then ultrasonic machining, then abrasive jet machining, jet of air plus abrasive powder, and then water jet machining, abrasive water jet machining, abrasive flow machining. That means what is the difference between abrasive jet and abrasive flow? In abrasive flow machining, abrasive particles are in some fluid, putty type of material. In that it is moving like this. So this is abrasive flow machining. Okay. In that we have and then magnetic abrasive finishing. Okay, that means magnetic field is controlling the movement of the abrasive particles. And then we have got magneto-rheological finishing. Okay, that means rheology of the material changes. Started putting so much sound by this one. So okay, and this is magneto-rheological abrasive finishing, elastic emission machining. It removes material with atomic level of accuracy by giving the workpiece a mirror-type finishing. In elastic emission process, a polyurethane material bar is used and is mounted on a shaft which is driven by a variable speed motor. So rotational axis is oriented at an angle of 45 degrees. That whole process is there, and it is they caused mainly by elastic fracture at atomic level. Now electric discharge machining, it is basically thermal process. Okay, so nowadays it has become common, very common. Wire EDM, almost each means many students, even polytechnic institutes are having wire EDM. Then wire electron beam machining, but it is very expensive machine. It requires the vacuum. And laser beam machining is okay, but laser has plasma arc machining, that is also thermal. But focused iron beam machining, here you see that ions are coming. Ions are very heavy compared to electron, so they are able to eject that material. You know, see, this is hitting and ejecting. And then FIB, electrochemical machining, ECM. This process in many countries they are now banning also, because it creates a lot of pollution actually, because electrolyte will be there now. So it also causes, if you release too much material, that is why that. So electro steam drilling, similar to that one. Chemical machining, only chemical is used. Photochemical machining, light and chemical. Chemo-mechanical polishing, hybrid process, mechanical and chemical combined. So other books are, you know, that there is my one book chapter is there in this one book. So in advanced machining classes, introduction to mechanical engineering, in that there is one book chapter, anybody can get that. So this will be mostly that complete that one coverage actually. Now let me just see that here. Okay, where is that thing? Yeah. So is there any question now? Now you can ask that something. Okay. Yeah. Yeah, Pathak. Yes. You can unmute and ask that something.
Sir, yeah. While sir, practical machining, that uncut sheet thickness, how will we measure? Because till now the tool has not yet cut it.
Uncut chip thickness, correct. Okay. So uncut chip thickness measurement, there are okay. Means one is you have to say first, suppose rather you say that how we will measure the chip thickness. Chip thickness is that one thing, that you know you can measure the chip thickness by length or by weight. And as far as the uncut chip thickness will be there, that there are many methods that suppose you are doing some operation, you can make one groove and you can find out the length of the chip, that you know how much up to the groove, that this will be the length. And the other method can be based on the weight actually. You take the weight of that thing, okay. And theoretically the uncut chip thickness will be related to the feed and cutting angle, okay. So there were many methods, like you know that in which chapter I had described that, I think PPT number this one. There are methods to tell, but anyway I am just reading it from here, that book also enumerating that here. Yeah, measurement of shear angle when we are telling, so we have written that during metal cutting you can make some assumption, of course, that length and thickness and width is equal to basically constant. And so if you want to measure the cutting ratio, it can be considered as the T by TC same as L by LC. So either you measure the uncut chip thickness or you measure the uncut length. Both are the same. Okay. So what happens measuring the chip thickness and the thickness? Now this method. So what happens that here? So they make one type of this one. I think did I make this case that suppose you make a saw cut. You are doing the operation of this one, so you can make a saw cut type of thing, so that you can know that up to this length my material has been cut. Other way was that measure the is an alternative method is to weigh a known length of the chip. Suppose you have taken one length and and establish the length of cut. So weight of the chip will be rho times LC into TC into BC, that you have weighed, and the same thing will be rho LTB. Okay, so rho is the density of the material. So rho can see. So therefore that known length. So therefore L will be equal to WC divided by rho BT. Okay, so that means the so it can come by that way. Okay, that means you can have this thing. So that so by that you can find out by measuring the weight of the chip actually. Okay, so these are the methods of this one. So yeah, so it is yeah, that is how that you can actually do this way. Okay, so it is from the evaluation of all from measurement of chip length is a better method, since chip thickness ratio is also equal to the chip length ratio. So like that we have to do that actually. But yeah, so yeah, so that is how that we measure the uncut chip thickness. That means two methods, weight and this one. I think I have described also here which one, that lecture 5 video. It was conversion of tool angle. Let me just show you that. This was lecture 6. Okay, this is mechanics of orthogonal cutting. Yes, cutting ratio. So you see that here you roughly get T1 by T2 merchant circuit diagram, but then it comes this one. It agrees this one effect of numerical example. This was it was here, and then FT is equal to, of course, that some rough estimate is T1 is equal to F. T1 is equal to F times this one. So naturally the uncut chip thickness should be related to the feed and this one, that this contact angle. So it should be based on that T1 is equal to this thing. This is your basically theoretical that chip thickness, uncut chip thickness, because F divided by this one. So this is a theoretical formula for T1, and similarly W is equal to D by cos psi. And then next chapter, this is a lecture number, it was what number? This is lecture 7. In lecture 7 I had told that strains and stress. No, not that. Strains and lecture 8, I think. In 8 it was there in detail. Experimental study. Suppose you want to study experimentally, then there are two methods. One is that you see that we are having a cut type of thing. So I already know that that one chip length will be only this much, 2 pi r, because periphery. After that it will be broken. So I have done a cut type of thing. So then I will know the length. Otherwise I don't know that how much it has, and increased length will be more. So that means I will just cut one revolution and I will get, let us say, some lengthy chip. Maybe I got say suppose 3 centimeter. Okay, but as such my calculation wise 2 pi r, it should have been this one. How much it may be? Maybe 2.2, because length will basically increase. Decrease. Length will increase. Chip contraction, because the thickness increases actually. So length will increase basically. So that means decrease. Okay. So that means actual maybe. So that is why it is called chip contraction actually. R is equal to T1 by T2. R is less than 1. So T1 is less and T2 is more. But the same R is equal to L2 by L1. So that means L2 is means cut length and L1 is uncut length. So uncut length will be this one. Uncut length will be this is uncut length. So uncut length will be more L2 by L1 na. So L2 divided by L1. Okay. So chip thickness is more, but uncut length is also more. So L1 is more. Okay. So that means suppose you measure and theoretically it should be 2 pi r. So you say suppose it comes out to be 2 centimeter, but when you measured it may be 2.5 centimeter. So you can find out the cutting ratio by this method. That was one method, but the other method was this also, that you measure the weight. So suppose I have measure the weight of some chip whose length is known to me. I know that length also, and maybe I know thickness also. Of course, thickness will be uneven, but we have this formula W is equal to rho L2 T2 W2. And the same thing has to be rho L1 T1 into W1 because weight remains constant. So therefore, we get a formula L1 is equal to W. That means if this is the weight, then this must be that type of situation, rho T1 into W1. Okay. And W is, anyway, W is, we are assuming that in orthogonal machining, W is constant, but in oblique, of course, both are changing also. So we can get the idea that what is the product of T1 into W1 by measuring that thing, that this much material has been cut. It is very easy to know that I have measured that material and I know that this much material has been cut. So now what is its dimension, that I can measure again. So this, and then we have to tally that whether experimentally it is coming T1 is equal to F divided by cosine psi. This way it is coming or not. And similarly, W is equal to D by cosine psi. Actually, it should be like that. But you know, there may be due to some vibrations or something, there may be some difference also. No? But otherwise, roughly, suppose your phi is equal to 0, that means tool is very straight. So obviously, your D, W should be equal to D, means whatever depth of cut you give, that much width you should be getting. No? That means that should be your uncut width. But practically, it may be little different, only slightly different. Okay. So that way you can do that. So weight method is the more reliable method by weight. Okay. Okay. So right, Pathakji? Okay.
Yeah.
Yes. Okay. So by weight method you can do that. Huh? Okay. Yes. Yeah. Welcome. Yeah, you are speaking something, but I am not able to. You have muted.
No. While during joining, I was trying to join, but I was not able to join it. I don't know.
Okay. You were not able to join that time. Acha. Okay. And now, yeah. So fine. So this is, let me just see that slide also. So there is nothing that this one. Assignments people are submitting that. How many?
That I cannot see the data.
No, but roughly. You don't have even idea that 1, 2, 3, 4.
No.
Is there any time that in which nobody submitted assignment?
No, that is not.
Acha, so assignment they are submitting actually. But exam, I think very few people will appear, about 20 people, you know. Pathakji, you have joining exam or not?
Yeah, I registered. No, I once WhatsApp you my registration, that payment receipt na for
No, that, but exam is separate, na. You must have, I think for exam you have registered or not.
Oh,
exam,
that no exam. I think I have registered. 1,000 rupees was there, na.
1,000, yes, fine. No. So then it is okay that exam will be there. So I think it is all right. Na? So this one, okay. So now almost, when is the exam?
26.
So 26 is the exam, and it will be what, in some center he has to go. Well,
I don't know.
they will announce.
They will give.
They will give.
I mean, they will send us some admit card or something like that.
But what, he has to come to Guwahati then?
No, he has some different location according to his, as per his location.
No, but his location is Dibrugarh, but in each place there may not be center, na? Okay, they will tell about the exam, na? Not many people are there in this one, so I think that they will tell, but you appear in the exam and then you can get, na? Okay, so fine, we can actually, I think we can leave that. Okay. Yes. Okay, fine, yes.
Yeah,
Okay.
thank you, sir.
Fine.